Hello, I'm Billy Younger. I teach physics and astronomy at Tidewater Community College in Virginia Beach. This summer I'm working for the Lens Project, and as part of my duties I've been asked to create this little presentation explaining to you what a physicist sees out in the field. In order for us to go out into the field, we'll be taking the Matthew F. Maury, a Vietnam-era boat that has been acquired by Tidewater Community College back in 1995. It's a 51-foot long vessel with a 13-foot beam. It has twin diesel engines and is a pretty nice piece of machinery. We'll be taking our trip from Little Creek. I believe we'll be moored in Little Creek Cove. We'll go out of Little Creek, out into the Chesapeake Bay. We'll go under or over, depending on what region we choose, the Chesapeake Bay Bridge Tunnel. We'll then go around the northern point of the south side of Tidewater area, down around the bend, heading south, and then go into Rudy Inlet as shown on this map. On our trip, we'll of course see within Little Creek Cove various military vessels and things of that sort. We'll also get to see the Chesapeake Bay Bridge and part of the tunnel and various tankers out in the bay, and ultimately we'll end at Owl Creek where we'll see some nice marshlands and things of that sort. While we're making that trip through the Chesapeake Bay, I had some thoughts as a physicist. First off, I know this is an interface between high salt content ocean and what I would assume would be a fairly low salt content estuary that is the Chesapeake Bay. The Chesapeake Bay is basically fed by the James River and other rivers, which are basically rainwater runoff from inland parts of the state. So at best this water in the Chesapeake Bay should be brackish, but at any extent I would suspect that it has a lower salinity than does the open ocean. With that being said, I expect some flow back and forth into the estuary from the ocean as well as out of the estuary into the ocean. And if the Coriolis force is in effect for this size of water mass, which I would suspect it is, then we expect all those motions of large bodies of water to actually deviate to the right since they're in the northern hemisphere. Since they're in the northern hemisphere and they deviate to the right, you might expect some of the increased salinity to appear on the north end, the west shore of the north side of the Chesapeake Bay Bridge Tunnel to have increased salinity. Additionally, you might expect a slight decreased salinity on the northern part of the southern end of Virginia Beach. So one of the things we could possibly do is determine how the salinity changes from the northern part of the bay to the southern part of the bay using various devices for determining ocean salinity. Another thing that comes to mind is the Bay of Fundy in Canada. The Bay of Fundy has the largest, most extreme tidal change in the world. Somewhat a debate on whether it's the best in the world or tied for the best. But either way, we believe part of the reason that its tides are so extreme from low to high, so on the order of 60 feet for instance, is because there's a resonance occurring at the mouth of the bay. Specifically, ocean waves come into the bay, reach all the way back into the northeastern portion of the bay, bounce off, and then come back. If that mixes just the right way with the incoming waves, you can get what's called a standing wave. And if that period of oscillation of that standing wave is comparable to the actual wave periods that normally occur as a result of the sun and the moon, then you'd expect a more severe tide. So you either need that period to be the same or one of its harmonics to be the same or very close to the same as the period of oscillation for the normal tides. With that being said, we have the Chesapeake Bay, which is an estuary. It's a lot longer but also quite a bit narrower, so we may not expect quite as severe of a tidal change, but we should be able to see some evidence by looking at the tidal data to determine whether or not there is any resonance whatsoever. So is it possible that the incoming and reflecting ocean waves could actually create standing waves whose harmonics affect the tides? Well, there's a very straightforward single equation that you use to determine that period and then see if it or its harmonics are comparable to the moon-driven tides. Here's last year on the boat. We had some people pulling in a net. I believe it was a net. And in the background, and this is actually the important thing, oddly enough, but in the background you'll see various waves. I'm just wondering what kind of waves those are. I have a suspicion, as do you, I hope, but there's capillary waves and there's gravity waves, also known as swells. I think you can suspect which types of waves these are, but we also have wave properties that are dictated by the depth of the water. So are these shallow water waves or these deep water waves? Either way, if they are shallow water waves, do they actually obey the equations for shallow water waves, or do they obey the equations for deep water waves? A very simple calculation. All we have to do is use a Logger Pro video analysis software with a little bit of video footage and some kind of object that we can use as a measure. So we can look at the actual wavelength and count out the frequency and then determine the speed and see if the velocity is indeed equal to the frequency times the wavelength, and if in fact it obeys the formula for a shallow water wave or for a deep water wave. So, are they gravity waves? Are they capillary waves? Are their speeds consistent with those waves? Are their speeds consistent with either one of them, for that matter? Another thing you might want to try is not so much forefront research, but it's certainly something that's a learning experience that you can enjoy as well as your students in the future. But I have a sextant. I have several sextants. We could actually use those to try to determine our position out in the bay. We could use just a handheld GPS device or even the devices on the Maury itself, and get an idea of what an accurate figure of our GPS is and see how precisely we can actually determine, using celestial navigation techniques, our location. Another thing, if you look at a satellite view of Rudy Inlet, you see it's a very narrow little inlet, and it's got a pretty big bodies of water behind it. Lake Wesley, Owl Creek, Lake Rudy, I believe, is another one. And you also look, once you get up in there, you'll see that there's definitely some tidal changes going on. So you'll see areas that are dry that you could tell normally have water, and then areas that are covered with water that normally are dry, all sorts of stuff. So with that in mind, with the tides always changing, we might think, since it's got that narrow restriction as Rudy Inlet, perhaps water goes through there pretty fast to change tides. We can get a rough estimate of what that is through some really basic arithmetic, and get an idea of whether that's a wave speed or a water speed that's too high to overcome for the average paddler that might be, say, stuck at sea. On the board the Maury, we have several devices for measuring salinity, one of which is called a refractometer. How exactly do those things work? We could ask, do they work with any type of salt mixture? For instance, could we use, for instance, a table salt pure water mixture to get an idea of the measured salinity and see if the refractometer could be calibrated that way? Once we get into Owl Creek, we can look at the difference tide makes. And it's commonly thought that basically the Earth's pull, or excuse me, the moon's pull on the Earth and the sun's pull on the Earth cause the section of water directly between the Earth and the moon, or directly between the Earth and the sun, actually causes the bulge that we know of as high tide. We also know that due to frictional forces, that bulge actually lags behind that line connecting the center of the moon and the center of the Earth and the center of the sun and the center of the Earth, and it's often quoted that it's about 3 degrees. Is that figure really accurate? That's something we can work out. We can also use some off-the-shelf planetarium software to find out what that angle is, and once we know whatever that angle is, can we use that to predict tides? In other words, we can actually take an off-the-shelf planetarium software such as the Sky or Skygazer or one of those type software packages and get an idea of where the actual sun and moon are, and see if that actually is consistent with this 3 degree figure that we're often mentioned, are told. Additionally, if you look at the same picture, you can see that these are slopes, and there's a lot of grasses and stuff growing on slopes. Plus, if you look at the more desolate areas of the beach, you'll often see sand dunes building up around reeds and grasses and things of that sort. So one of the things we could do is see how effective plants really are to prevent erosion. Are they as effective, for instance, as riprap, which is what we often use in engineering, and for instance, the Department of Transportation uses as well. One of the final things, one of the last two things I should mention when you get out to Owl Creek is you'll see that the plant life changes from location to location, not only because of amount of water or amount of wind, but also because of the amount of sunlight. So we could use a radiometer or some other measuring device for measuring ambient light and see if that's predictive of what kind of plant growth there is. So that's another idea you can investigate as a person wanting to apply physics out in the field, especially at Owl Creek. Finally, the last thing is, last year when Rich dug us some nice wells, we discovered that the water table had actually various depths. In some cases, you'd find that the water table would actually be higher than the water that's actually sitting in the ditches and in the lake, or the creek, that is. We can also find areas where it's lower. Can we actually explain these increases in water table depth and decreases in water table depth from things as simple as surface tension and capillary action? So that's some of the ideas that I've come up with. There's a few more as well, things that you could consider on your own. But these are some of the things that I've thought about when I got here. Just to recap, some of the things we could address is, does the Coriolis effect cause increased salinity on the north side of the Chesapeake Bay, or can we see standing waves in the Chesapeake Bay tides? What do wave speeds tell us about the waves? How accurately can we determine our location with a sextant? How fast does the water travel through Rudy Inlet? How do refractometers work? Can we calibrate refractometers using just basic salt and water solutions? Can we predict tides? Are plants affected to prevent erosion? How does ambient sunlight affect the survival of plant species? And finally, can capillary action explain varying water table depths?